15.5 Equilibrium calculations. A closed system initially containing 1 times 10 to the negative third molar hydrogen and 2 times 10 to the negative third molar iodine at 448 degrees Celsius is allowed to reach equilibrium. Analysis of the equilibrium mixture shows that the concentrations of hydrogen iodide is 1.87 times 10 to the negative third molar. Calculate the equilibrium constant at 448 degrees Celsius for the reaction taking place, which is shown here. So what do we know? It's very helpful to set up a table like this one with the initial concentrations, the change in concentration, and the concentration in equilibrium. Of course, we need the concentrations at equilibrium to solve for the equilibrium constant expression. So we were given the initial concentrations of the two reactants, 1 times 10 to the negative third molar in hydrogen and 2 times 10 to the negative third molar in iodine. And there was no product present initially. We were also given the equilibrium concentration of the product, 1.87 times 10 to the negative third, and then therefore we can figure out what the change was. So we must have added that quantity to the concentration. The stoichiometry in the reaction using the coefficients tells us that hydrogen and iodine will decrease by half as much. So we therefore know the concentration change to be a negative 9.35 times 10 to the negative fourth. And then we're therefore able to figure out the concentration of the reactants at equilibrium and apply them to the equilibrium expression. So we know that we're using products over reactants, and plugging those values in that we just found, we can calculate K sub C. Sample exercise 15.8, calculating K when all equilibrium concentrations are known. It's a very nice, easy problem when we know all the equilibrium concentrations. It makes it very, very simple. So here we have a mixture of hydrogen and nitrogen, again the Haber process, reacting in a vessel allowed to attain equilibrium at 472 degrees Celsius. The equilibrium mixture of gases was analyzed and found to contain 7.38 atmospheres hydrogen, 2.46 atmospheres nitrogen, and 0.166 atmospheres ammonia. From the data, calculate the equilibrium constant, K sub P, for this reaction. All we have to do is use the balanced equation, write the equilibrium constant expression, products over reactants. We're substituting in the equilibrium partial pressures into the expression, and we solve for K sub P. Do the practice exercise. Sample exercise 15.9, calculating the equilibrium constant from initial and equilibrium concentrations. Okay, we've already done sample exercise 15.9 in the previous slides, so we're just going to skip to the practice exercise. It says sulfur trioxide decomposes at high temperature in a sealed container. Initially, the vessel is charged at 1000 Kelvin with SO3 gas, a partial pressure of 0.5 atmospheres. At equilibrium, the SO3 partial pressure is 0.2 atmospheres. So I want you to calculate the value of K sub P at 1000 Kelvin. Try that now.